All right, welcome juniors and only juniors to week 17, video 1. I'm only doing one video, so it might be a bit long, where we're just going to take a look back at what we have used already this year and previous years in our limits. And we've talked about continuity as well. This is the textbook that you'll be seeing next year in your AP Calc class with Sanford. And we're just going to do this. We usually have about 3 or 4 weeks at the end of the school year for this unit, but because of everything going on, we have a very condensed version of this unit where I just want to stress again the limit notation, what it means, and just a little preview of how you're going to use it next year in calculus. So let's jump right to it. I want us to look at this very college level definition of what a limit is. So I'm going to read it word for word, and then I'll describe it in a bit more what I think is approachable language. So let's look at this. The definition of a limit. Assume the function f is defined in a neighborhood of C, and let C and L be real numbers. The function f has a limit to L as x approaches C if, given any positive number epsilon, there is a positive number delta such that for all x, 0 is less than the absolute value of x minus c, which is less than delta, then the absolute value of f of x minus L is less than epsilon. We can write that as that notation, which we say the limit as x approaches c of f of x is equal to L. So that's the math book definition, that's college level. Honestly, I did not ever learn about this delta and epsilon until graduate school. So we're not going to talk about it. But we do need to know what that limit notation means. What it means. We're not trying to find f of c, right? We're not trying to actually find the function at that value. We're trying to find what is it approaching, what is going on around that value. So for a limit, and I do like this word here, the neighborhood. So for a limit, we never look right at the value they give us. We look around that value. So let's see why we do that. So here is a function that we're going to take a quick look at. We have this function, f of x is equal to the sine of x divided by x. We have this function graphed and a table for it over here on the left. And we can see, we'll take a look at that in a second. But we can see an issue with this because if we try to plug in 0, we get the sine of 0 divided by 0, right? So we would get the sine curve, we get 0 divided by 0. We don't know how to divide by 0. So we can look at the graph instead because we only have that issue exactly at x is equal to 0. So if I zoom in as much as I can, right, we have -1, +1, +1, and 0. We can look at 0.5, right? X is equal to 0.5. And that can kind of get us a closer idea. We can look at x is equal to 0.1, and we can get a closer idea. We can get closer and closer and closer eventually to where we get like f of 0.001 or f of 0.000001. We want to keep getting closer and closer to that value that's right next to the arrow, but never actually get to it because that's when we divide by 0, and we can't do that. So if we zoom in, we don't even need to zoom in that much, we can see in this graph that as we get close to x is equal to 0, the y value is going to be equal to 1. There's not really that crazy of a thing, right? As we go towards 0, as the limit of x approaches 0 of f of x, we get 1. That's what the graph looks like. If we graph this in the graphing calculator, we might not even ever notice unless we went to the table, that we get an error at 0 because the graph looks quite nice, right? And we have talked about these issues before. When we did rational functions, we talked about when we could have those discontinuities when the denominator was equal to 0. But we're just reviewing right now, right? So we can see how we've used this before. We can't plug in 0 because we'll get an error. Instead, we got to look at the graph or look at the table around 0, in the neighborhood of 0. So the book goes on, and I'm not really too happy with how this book lays out for us, especially with our very constricted time frame. But I did give you a couple of assignments on Khan Academy that we can build off of what they have here so far. So what we're going to do one second. I don't like how, okay. Anyways, so we have our limit notation. So let's just take some notes. So limit as x approaches a of f of x. All right, the book says capital L for that. But what that means is, what does the function appear to be around x is equal to a? Again, they use that word neighborhood. We're not looking at x is equal to a. We're looking around it. We're looking near it. We can see that in a graph and in a table, and sometimes our limit does not exist. So we can draw some examples of that. Okay. If I said, what is the limit as x approaches 3 of this function, we will look at our graph, right? We can draw a vertical line at x is equal to 3 to help us out. There's not a consensus here, right? On one side we're going up, on the other side we're going down. So this would be an example of where our limit does not exist. The graph is not clear. It's not equaling to something on either side. It's not that there's a gap in the graph, it's that there is a big disconnect between the sides of this equation. Or we could get one where we have something like this. So what is the limit of x approaches 2 of this function? And if we look at this, again, we can draw a dotted line at 2. And we can see there's no consensus. If we look at one side of that dotted line, on the other side, the function jumps, right? And that is something that we learned about, but now we're trying to rephrase it and use our limit notation on it. Our limit would not exist because we have that jump. We have that shift between the two parts at that value. So make sure you're paying attention to that. We can also see that in a table where if we have a table, let's say we have 0.7, 0.9, 0.99, 1.01, 1.1, 1.5, and so on. So let's say here's f of x, here's x, and f of x would do something like this. if we look at this, right, if we were trying to find the limit of x approaches 1 of f of x, right, we're trying to figure out in between those two values, because that's where our x is at, what we could try to figure out. And here we can see another gap, right? It goes from 4.1 to 2.9. That's a gap. There's not a good answer here to what our function would be at. So our limit of the function does not exist because there is that big gap between numbers that are really close to each other. So if we keep discussing this, I think graphs we can do quite easily. Tables it might take some thinking about because we have to visualize it, especially when it jumps from one number to another one that's very far away. But let's talk about how we could actually create a table like this. So let's say I wanted to find the limit of x approaches 5 of f of x. What I would want to do, right, is I would want to pick numbers that are very close to 5 on both sides. So maybe 4.99 or 4.7 or 4.5. We're getting closer and closer to 5 from below it. Or like 5.02 and 5.15 and 5.4. As long as we're getting closer and closer to the 5 number from both sides, we're good. So usually what we show in our book is like 4.9, 4.99, 4.999, 5.001, 5.01, and 5.1. That's like the golden standard of what level and how we approach it. But the example here on the left with these little bit odder numbers are just as good. It can provide us with an idea of what the value approach is. So you will have a Khan Academy that's about creating tables, and we want to make sure when we create tables, we have numbers on both sides very close to the value that x approaches. All right, so here I said x approaches 5, so we tried to find numbers that are very close to 5. A bad example would be if we did something like this. Right? We look at this table, we have numbers that are on both sides of 5, but nowhere close to 5, right? And by close, I mean decimals away. This, not decimals away, way too far away to actually try to find the limit. A lot of crazy things could happen. We just don't know because we're not looking close enough. We want numbers that are very close to 5. And then the other thing I wanted to talk about is, and this one we can look at the book real quick for it, is what we call one-sided limits. So we talked about the function, what happens around that value, but as we even saw in that example that I provided, sometimes either side could be different, right? And the way that we work around that is with saying, well, what if we only look on one side at a time? Right? So what if we looked at only the left side and said, what's the limit on the left side of that value? And then we say, well, what's the limit on the right side of the value? And then we compare the two. You're not going to have to compare the two this week. We'll talk about that next week, week 18. But that's what we're going to talk about next. It's called one-sided limits, and we actually have special notation for it. So the notation that we use, I'm trying to zoom in a lot, is instead of just x is approaching c, now we have this extra symbol by c. That's like a positive sign in the exponent. That means as we approach from the right, right? Because positive numbers on the right-hand side of a number line. If we have that positive number, that means what's going on to the right of the graph next to C. If we have a negative symbol in the exponent, we're saying what's happening on the left-hand side of that limit. So if we look at this example here, we're going to compare the limit as x approaches 3 from the right of our function, which is intx, or what's going on from the left as x approaches 3 from the left, that little negative symbol of intx. So when we do this on a graph, and you will have examples on Khan Academy from a graph and a table, we want to very carefully, and I would do this if you could, draw a vertical line at x is equal to 3 to try to place it, and so you can see what's on the right, what's on the left. So let's just start on the left. If we look at the left-hand side of this graph, right, here's the left-hand side, we want to find the part of it that's the closest to our vertical line. So I can zoom in, zoom in, zoom in, right? And we're looking at this one right here. That is the closest to the vertical line. It's decimals away from x is equal to 3. And if we find the value, right, it's equal to 2. So the limit on the left-hand side is equal to 2. But if we look at the right-hand side now, right, so if we zoom out, we can see this is the right-hand side. If we zoom in, zoom in, zoom in, get closer and closer to 3 decimals away, we can see that it approaches a value from the right, and that value would be is equal to 3. So here's an example where our limits don't match. So on the left, it's approaching a value. On the right, it's approaching a different value. And that is an example of how we can have a limit on the left and a limit on the right, but together they don't match up. So the limit does not exist overall. So the way that we write that, and here again, this is a good introduction to what math books will look like for you in college, where we have this very convoluted statement. A function f of x has a limit as x approaches c if and only if the right hand and the left hand limits at c exist and are equal. The symbols, the limit of x approaches c of f of x is equal to L if and only if, that's the symbol for that. The limit of x approaches c on the right of f of x is equal to L, and the limit as x approaches c from the left of f of x is also equal to L. So both need to exist, and they need to be the same. So an example of a graph where we could do a lot of different examples, right? We can say the limit as x approaches 1. We want to know what that is. So we would do what I've been describing, right? We can draw a vertical line, and we can say the limit as x approaches 1 from the right of f of x. So we look on the right, that would equal to 1, right? The limit as x approaches as x approaches 1 from the left of f of x. And now we look at the left, and as we get closer and closer to that vertical line, our y value is getting closer and closer to 0. So here we have two limits, one on the left, one on the right, but they're not the same, right? 1 is not equal to 0. So our limit for x approaches 1 does not exist. So what I need you guys to try to practice is just doing those, looking at graphs and tables this week, and practicing that new notation. All right? And it's very important to really pay attention. If I give you a limit, right, you need to look up here to see what's going on. If there is nothing there, you need to check both sides. Right? If there's a positive, you only check the right side. And lastly, if there's a negative, you only check the left side. So be careful when you're doing the limits Khan Academy will give you a clue because it says one-sided or nothing, right? One-sided, you have to pay very close attention to if it has a positive or a negative, because the answers will be different depending if you look on the right or the left. So that should cover everything that's asking on Khan Academy. If not, send me an email and I will let you guys know. I will be available Wednesday between 1 and 2 for class Q&A. And there will be a couple of you presenting, but it'll only take maybe the first 15 minutes, the presentations. So if you need to come and ask a question about the Khan Academy or these notes, feel free to do so then. Good luck.